Okay, we're going to write an algorithm to flatten a multi-level linked list. So to do this, what we ultimately want to do is have a result that is sorted so that if we had a list that looks like this with 5, 10, and 19 being the rights of each other, and then 5, 7, 8 is the down, so each node has a dot right and a dot down, then at the end we would want something like 5, 7, 8, 10, 19, 20, 22, and 50. So that would be what our resulting linked list would look like. So what we're going to do is we're going to first traverse all the nodes, and we'll put them into a max heap so that we can then put them in the correct order. So to do this, we need to first make a node. Well, actually, we'll do a whole linked list class. Okay, and that is going to have a head. It's going to have a node class in it. Okay, and in that we have we'll call it right. Okay, we've got right. We have left. No, not left. We have down. And we have data. And those are ints. Okay, and our declaration would be, our constructor is going to take in the data and it will set data. It will also say right equals null. Just say right equals null. Right equals null. And down equals null. Okay, and then in our linked list, if we have a function add node, it's going to take in the data and we'll have node n equals new node, and it takes in our data. And then if head equals null, it means this is the first node in the list. So then head equals n. Else n dot next equals head, and head equals n. Okay, because we're going to add to the front. All right, so that will do for our linked list class, just so we've got that all down. And then what we want to do is we'll have our we'll have our function. It's going to return a node. We'll call it flatten. And it takes in our a node, which will take in the root or the current. So the first thing that we'll want to do is traverse. So actually, let's also have our traverse class. Our traverse function. And it's going to take in current as well. So if current does not equal, if current equals null, then we'll return. Otherwise, we're going to traverse current right. We're going to add to a max heap that we need to create. Enqueue the data, current's data, and then traverse left, which is down. So there's our quick traverse. Okay, so before we can call these functions, we're going to have made our priority queue. We need a little more space than that. So let's just call this that we have a class called, we don't need a whole class, but let's say in our main, we have our priority queue. This. Okay, we have our priority queue. We'll call it max heap equals new priority queue. And we will need to, and that's, we'll do it of ints because we're going to put the data in that. Okay. And in that, we need to set a comparator so that since we're making it a max heap and since the default comparator goes to at a min heap, so this way we can return, or we can order these correctly. So we're going to compare B and return B minus A. Okay, so we've got our priority queue set up. We've got our flatten function. And so in flatten, we would first traverse our list. Then we need to make a new linked list. So linked list, we'll just call it LL equals new linked list. And then within that, we want to say, well, max heap dot count is greater than 0, then we know ll dot add node. We have to remember they're adding to the front. So since these will come out as a max heap, the largest first, it'll be perfect because we'll keep adding on and the lesser values will end up at the front. So max heap dot dequeue. Okay, so that's going to add those. And then at the end, we're going to return linked list head. Okay, and so actually in main, we can call, I didn't need to put this, I didn't mean to put that function in main. Let's just move it out of there. Okay. So here's main. And in main, we can say, we can make a new linked list in here. New list is going to equal we don't need to go through all the creating. We'll say that we have a linked list already, and it's going to go and be sent into Flatten. So we've got Flatten is going to take our current LL's head. And we need a new linked list for that. New list equals, and Flatten will be after that. So that kind of all goes together there. All right, so let's see how this goes. So if we use our current chart, and we will just keep track of it. First, we'll traverse it. We'll keep track of it in kind of a stack kind of fixture since we're using recursion. Okay, so to start, we start in current is going to be 5. That's what's going to be passed into this. That's going to be the 5 node. That's going to be passed into this flatten function. So it goes in and it calls traverse, and it gives us the root, which is that 5 node. So to traverse, it takes no current. If current equals null, return. It doesn't equal null, so traverse current dot right. So what I'm going to do is just keep track of where I'm at. So 5 node is there. And we're going to go right, which really is, oh, you got it backwards. We're going to go down first. Okay, so first we're going to go down. So on 5 we go down, and we get to 7. 7's not null. I'm going to put this here. 7 goes down. And now we're at 8. 8 goes down. And then it's going to go around again, but current will equal null because 8's down is null. So then we go to the next step, max heap enqueue current data. So we're at current here, and we'll just keep track of our heap. Here. So it gets added to our heap, and then it looks right. It doesn't have anything right. So we've finished that node. Now we're back at 7, and we're here, 7 in the current, means we add it to our list. And I'm just making it as a list, even though it's a heap, but 7 is going to be less than 8. And then it's going to look right of 7, and there's nothing to the right. So we've completed that cycle. We get to the 5, and it's going to do its current. So it's going to print here, or it's going to enqueue to the priority queue. Then it's going to look right. Okay, and so it goes right, and then we don't need to look at the 5 anymore because we've got the 10. And then the 10 is going to go down. So it's going to go to 20. And the 20 is going to look down. It can't go down, so it's going to go current, which means it's going to be added to the heap. And then it's going to look right, which is null. So we're done with that one. We go back up to the 10. It goes current. So 10 is going to be added to our list. And then it's going to look right. And it's done with that. So now we're at 19. And it's going to go down. It's going to go to 22. And 22 is going to go down. It's going to go to 50. 50 is going to look down. There isn't anything. So then it's going to look at it. It's going to do the current, which means that we are printing the 50. Okay. And then it's going to look right. There's nothing there. So it gets out of that. We go back to the 22. It's going to be current. Going to print 22. And then it's going to look right. And it doesn't have anything. So we're done with that. And get to the 19. It's going to be current. So we add the 19. And then we look right. There's nothing. It's null. So we get out of that. Okay, so now we have our list, our max heap filled up, and it is in the correct priority. And then we go through, and after we've been done with the traversing, then we've got our new linked list that we're creating. So we can create that down here, LL. So while max heap.count is greater than 0, we're going to add node to LL, max heap.dq. So the first one is 50. DQ that. It becomes a node. That's going to be null. And then the head is going to be pointing here because it's our first. Okay. Then we go to the next one because count is not 0. It's 22. DQ that. It makes a new node. And n.next equals head. And then head equals n. So now head is here. And then we go here. Max heap is still greater than 0. We DQ the 20. We get 20. It's going to point here. And the head's going to become the 20. Then we go through. Max count is still greater than 0. We DQ the 19. Okay, and then 19 is going to point to the 20. And our head is going to change. Okay, we keep going. 10. points at the 19. Our head is going to change here. Keep going. 8 points to the 10. Head is here. Okay, 7 points to the 8. 8. Head is now 7. And 5 points to the 7. Head is now 5. And now max heat.count is 0. So we get out of that while loop and we return LL's head, which is this node right here. And they are in order 5, 7, 8, 10, 19, 20, 22, 50. So we are good on that front. So the complexity of this is O of n plus n log n. N log n is for adding in and sorting in the max heap. O of n is because we have to look at every element. And then we have space, which is an O of n space because we had to use additional storage. And that should do it.